Hi everyone, welcome again. One of a student asked the following question after continuing my presentation. Let introduce the question of these friends. Let I be a monomial ideal, and f in I. He or she extract the question from the one of the proof of theorem. So let I be a monomial ideal and if in I, then we can write if sigma fi ui I 1 to m uh, fi in R and ui in I, because ui is the monomial ideal generated by monomials. Fi is a polynomials in R, in I here. So the question is why support F contain in this union I 1m support of Fi ui. This is the question of one of student in the class. Let F F in every Fi in R. So we can write Fi, as you know, Fi is R Ij V Ij such that Rij in K and Vij monomials in R. So Fi is as follows. So F is equal to sigma. This is in here. Vi, again, Vi in here, Vij in monar. So F sigma I 1 to M sigma. Let me write here. Fi ui, and so sigma I 1 to M. In here, Vi j in monar R Ij V Ij and Ui, writing in as this. When we looked at the summation, in this summation, maybe some of the coefficient summed and some of coefficient maybe cancelled, and so the support of F, when we support of Fi in here, support of Fi ui is equal to support of Fi ui. None of them is cancelled because when we Fi writing as this summation, so Rij is non-zero. In here is non-zero. So in this here is non-zero. But in here, when ui Fi in here, maybe some of the summation is cancelled or removed. And so if none of them none of them coefficient is or none of them coefficient is not removed, then we have the support of F is equal to this one. But the support of in here, if you look at this one, support of F and look to the here, so the support is the contain or maybe equal to the support of Fi UI I 1 to M, right? As this one because the monomials. In the proof of this theorem, and let me remind some key point that yesterday speaking about them. One of reminding some of key points because I need in this section in this in today I need some this kind this pointed. Let I, J, and K be a monomial ideals of R, then this is very helpful for the primary decomposition. I plus G intersection K is equal to I plus G intersection I plus K. This is only for monomial ideas or graded ideas. For graded ideals, it's true. So if Ji and J1 and Jm be a monomial ideal, be monomial ideals, then I plus intersection Ji is equal to intersection I plus Gi. I 1 to n. This is very useful for decomposition of monomial ideals. And the second, if I is equal to a monomial ideals U1, Um is a monomial ideal is a monomial ideal and V is a monomial element. Then I colon V is equal to summation of 1 to M UI colon V. This is equal to this one. And in particular, I V is equal to UI GCD U and V UI and V UI divided to this one GCD. GCD UI and V. That's that I 1 and F is equal to this one. And also And also note that every every monomial, see, every monomial, every monomial prime ideal of R is as form of P x1 and x I1 and x IM. Every monomial prime ideal has this form. And the only maximal ideal and M x1 and xn is the only maximal monomial maximal ideal. Monomial maximal ideal. And so every polynomial has exactly one maximal monomial ideal. One maximal monomial ideal has many maximal ideal, but monomial maximal ideal just one. And 5 and 4, every square free monomial ideal is a radical ideal. This is the uh, one of the end of theorem yesterday proved. Radical ideal means I radical I is equal to I. This is means of this. And so we continue the my presentation. Proposition starting by following proposition. Let I be a monomial ideal I be a monomial ideal of R, then radical of A, radical I is monomial. So proof. Suppose you know that every monomial ideal is finitely generated as a Dixon lemma. Suppose I is equal to y u1 and the u r such that ui is equal to x I1 r I1 x I r I r r chi. Yes. For all I want to r and ri chi is non-zero. Ri chi is non-zero. The power of the in a variable is non-zero. All of power. We prove that radical I is equal to this one. V1 VR such that where Vi is equal to xi1 and xi ki, the square free. For all I1 to R. So set Ri maximum of look to the power maximum of the Ri. Rij, Rit, Rij such that J 1 to Ki, the maximum of this one. And then V power Ri contain in I, because when we look the Ri, so Ri the maximum of this one, and every Ui in here, so V power Ri, this one divided the V power I, so Vi belong to I. And set L is equal to I 1 to R Ri minus 1 plus 1. This is the number and this is the number. Since F1 V1 FR VR plus power L is a sum of terms GI VI V1 D1 V2 D2 and VR dr such that the sigma of di 1 to r is equal to L. Every element in here power of L as the sum of these terms. So we have Ri less than or equal to di, this Ri, because if for at least one, because I between 1 to R. But because in other ways, and if every Ri bigger than di, we have this one. For other ways, sigma Ri bigger than di for all I between 1 to R. And so Ri minus 1 bigger than equal to di. So the summation 1 to R of this number bigger than the summation of 1 to I. This one L, this one set, look to this here, L is equal to this number. So this sigma is equal to L minus 1. And so L minus 1. This is the contradiction. So this is true. And so every I, for at least one I is less than DI. So when one DI is bigger than I here, so every term in here belong to I. Therefore, every term belongs to I, because they bigger than this one, and every term belongs to I, and so V1 VR power uh, power L contained in I, because every term of this ideal belong to I, and so this ideal power L is in I. And I is contained is V1 VR, because this is this ideal, every VI writing as this expression, and so VI divided DI, and so VI belong to VI, and this element contained here. Oh, we have this one, and we get radical V1 and VR power L contain, because the radical ideal, the radical ideal, if you have two ideals, then the radical is the forward, is the straightforward radical I contained in radical J. Always we have, this is easy. So this is radical I, this is the radical V1 and VR. So, and since when we look the left hand, we have V1 VR power L is equal to V1 VR, and this is square free. As the three-ways lemma, we have is equal to VR. And note that every ideal radical of every ideal power T, every power, so we have these two ideal is equal. So this is one equal to this. And so when we back to the above equation, above inequality, this is equal to this, and this one is equal to y V1 and VR. This is equal to, and the equality holds. And so radical of A is equal to V1 and VR. And this said that radical ideal is a monomial ideals. Also, the radical ideals is the square free. The radical ideal is a square free. So when we looked at the proof, look to the proof of this proposition, and previous lemma, we conclude the following theory. We have the following corollary. A monomial ideal I is a radical ideal if and only if I is square free, is a square free, a square free monomial ideal. So if I is square free is I is square free as a previous lemma, I is radical ideal. In the previous lemma yesterday proved that if I is square free, radical ideal is ideal is a radical ideal. And if I is a radical ideal, if I is a radical ideal, the radical ideal is square free. Every monomial radical ideal is a radical ideal. I is a radical ideal and is square free, generated by square free. So I is square free. And this is the equivalent. This equivalent is satisfied. So examples. Let let I is equal to x1 power 3, x2, x3 power 2, 3, and x2, x3 power 3, power 2, and x2, x4 power 2, 4, power 2, and x4 power 3. Then radical ideal as this theorem. The radical ideal is equal to V1 VR. V generated by VI is equal to this. The radical of the power is removed. So is equal to x1, x2, x3, x2, x3, x2, x4, and x4. So this one cancel because the x2, x4 is contained in x4. So we have two of them, and one of them is cancelled. So we have x1, x2, 3, and x4, the radical idea. And so write x1, x3, and x2, x4 as an intersection. Intersection of prime ideal. Prime ideal. Come back to reminding in the first of my presentation. x1, x3, x2, x4 is equal to x1, x3 plus x2, x3, x4. This one x4, x4. So this one equal to x1 intersection x3, and this ideal 2, 4 by using the in the first presentation, you see that reminding some key point theorem. This is equal to x1, x2, 4. Now is intersection x3, x2, 4. And again, for this one, okay, and again for x2, x4, writing intersection, and this is equal to x1, x1, x2, 4, x2, 4, the writing an intersection plus x2 intersection x4 intersection x x3 plus x2 intersection x4. So in the first we have x1, x2 intersection x1, x4. This one is equal to in the below, and so in the this one is equal to x3, x2, and x3, x4, and we have so x1, x3, x2, x4 is equal to x1, x2 intersection x1, x4, and x2 to x3 and x2, x4 equal to this. So, and in 3, write I is equal to x1, 3, x2 power 2, x3 power 3, x2, x3 power 2, and x2 power 2, x4, and x4 power 3. As an intersection, as an intersection of ideals of shape x I1 n1 and x I k n k. You want to this ideal as an intersection of this ideal. So again, using the key point I, this is the proof. So I x1 3, x4 3, this is I x4 3 plus this ideal x2 2, x3, 2. Let me write x2, 2, x4 is ideal plus x1, 3, x2, 2, x3, 3, and x2, 3, x3, 2, and x4 power 3. This ideal is equal to intersection x2, x4. This is equal to x2 power 2 intersection x4. And using the key point, we have x2 power 2, x1 power 3, and x2 power 2, x3 3, and x2 3, x3 2, and x4 3. Intersection x2 x4 x1 3, x2 x3 2 3, and x2 x3 3 2, and x4 power 3. So look the first monomial ideal. This one cancel because this one containing here. This one cancel containing here. So and look the second monomial ideal. This one cancel containing here. And so we have so is equal to x1 3, x2 2, and x4 3 for the first. And for the second, we have x1 3, x4, and x2. The second writing again the same of the we want to use the key point, and x2 2, x3 3 plus x2 3 intersection is one is x3 2, and this ideal is equal to intersection x2 2 3 intersection x3 power 2. Again from the key point is the first ideal is the same 3 2 and 4 3. So the second ideal is x1 3, x4 x2 2, x3 3, and x2 3 intersection x1 3, x4 x2 2, and x3 3, and x3 power 2. And this one element containing here. So we have x1 3, x2 2, and x4 intersection. This ideal we can write as a key point. People are using the key point in the first remainder. 3, 4, 2, 3 plus x2, 2, and 3 intersection x1, 3, x4, and x3, 2. So we have x1, 3, x2, 2, and x4, 3. Intersection this one is equal to x2, 2, intersection x3, 3. So we have x1, 3, x4, x2, 3, x2, 2, intersection x1, 3, x4, and x2, 3, and x3, 3. And also in the end, so this one can still belong to here. We have this 3, x4, 2, and x4, 3. Intersection, uh, is this the same? X1, no, this one, 2, yes, I cancel in the end, x2, 2, and x4. Intersection, this one is x1, 3, x2, 3, x3, 3, and x4. Intersection, x1, 3, x3, 2, and x4. So this ideal, x3 here and x2 here and x4 here. So this ideal smaller than this ideal. So the intersection, consider this one. So this one is cancelled. So, and here x1, 3, x2, 3, x3, and x4. So if this one is not here, and x1, 3, x3, 2, 3, 2. So we have three of them. x1, 3, x2, 3, 2, and x4, 3. 1, and this one, x1, 3, x3, 2, and x4. Yes. And x1, 3, x2, 3, x3, 3, and x4. Yeah. The ideal is equal to this. The, the composition. This is the composition. The same of the number. When we look to the number, for example, 12 is equal to 2 power 2 and 3. For example, 24 is equal to, this is the prime number. This is the same. This is the, in the continuing, we see that this ideal is a irreducible. This ideal irreducible. This ideal is irreducible. And so in here is 3, 8. So equal to 3, 2.3. Yeah, the same of there's the same of the composition of the numbers. So Definition: a monomial ideal ideal I is called irreducible. Is called irreducible. Irreducible. Irreducible if it cannot be writing. The writing cannot be writing as proper intersection. Proper intersection of two other monomial ideals. Two other monomial ideals. Otherwise, if I as a, contain as writing as a two proper ideal, proper monomial ideal, then said is called reducible. Is called it's called reducible. Reducible. In the previous example, this ideal is reducible, writing as an intersection to bigger ideal. And in here, this ideal is reducible. I is a intersection of three ideals. But this ideal, when we looked at the ideals, these ideals, the prime ideal is irreducible. For example, every prime ideal is irreducible. Every prime ideal is irreducible. And a presentation, an ideal version of an ideal I as I equal to intersection of Qi 1 to R 1 to M of ideals is called irredundant. Irredundant if none of the ideal Qi can be omitted in the presentation. For example, if you look the previous example, this is the irredundant primary, irredundant decomposition of A. None of them is cannot be cancelled. And also in here, this is the irredundant decomposition. And all of the ideal is irreducible. This ideal is irreducible. Is irreducible, irreducible, and irreducible. Every prime ideal irreducible, and every ideal here we prove that this one every power, pure power of every idea generated by pure, pure power variables. This is is irreducible. Irreducible. So, we write the following fact. If you have a questions or comment, we can send email for me and immediately answer to your questions. Fact, let I be a monomial ideal. Be a monomial ideal. Be a monomial ideal of R, then I equals to Qi I1 to n when Qi is equal to x I1 I and the pure power xi k k power k. This is a very nice fact. This is a theorem, a very nice theorem, but I write it as a fact because I want to using this fact. So monomial ideal, every monomial ideas has a presentation as a intersection of the irreducible ideals for all uh, I and M. Moreover, moreover, an irredundant presentation irredundant presentation is unique U. Presentation of this form is unique U. Yeah, and if you have a presentation for ideal as a irreducible ideal, and this presentation, if reduce is irredundant, so is unique U. Every irredundant presentation for one ideal for ideal I is equals. So theorem. We want to prove this one. Every ideal generated by pure power variables is irreducible. We want to prove this one. A monomial ideal. A monomial ideal I is irreducible if and only if up to presentation up to permutation of the variables variables, variables I can be written as I x1 r1 and xr r, where ri bigger than 0 for all I. So every irreducible ideal has this form. It's very nice. And so the irreducible ideal in monomial irreducible ideal is known as this one. So for the proof, let I equal to x1 r1 and x r r. And suppose I is equal to I1 intersection I2. My assumption is I has this form. We want to prove that I irreducible. Assume that I is reducible. We want to find a contradiction. We want to find a contradiction. So where I1 and I2 are monomial ideals. Ideals properly contain I. We, we want to find a contradiction. I is a monomial ideal writing as intersection of two proper monomial ideals. I1 is monomial ideal. Look the fact, every monomial ideal has a unique U presentations, unique U irreducible, redundant presentation. So for I1 has this present. We have I1 is equal to I1 to R, and I2 is equal to intersection of Q prime I 1 to S. So where Qi and Qi prime are generated by power of the variable, power of the variables. Thus, I is equal to intersection of Qi 1 to R and intersection Q prime I 1 to S. Then by omitting suitable, by omitting suitable ideals in this intersection in the intersection on the right hand, right, we obtain uh, you obtain an I redundant presentations. So presentation of I. So the unique use the unique use statement in the above fact we have two a redundant presentation for I. One presentation itself uh, of I, the other presentation is one. So the unique use set this ideal equal to one of the QI. And so is then fact implies that I is equal to QI or I is equal to QI prime for QIJ for some I or J. And this is a contradiction, because the intersection is equal to this one. And so we don't have a two bigger ideal, I1 and I2. We don't, because it's the proper ideal. I1 and I2 is a proper ideal contain I. So, but if I is equal to, then the ideal of I1 containing I is not the proper, is equal, is a contradiction. So for conversely, and so I is a irreducible. I is irreducible. And conversely, if we want to, if I reducible, we want to prove that I is this form. Assume that if Ji contains a monomials, one of the generated of A, assume that is not a pure power. We assume that is not pure power. If Ji contains a monomial U V W such that GCD V W is 1 and V is not equal to 1 and W is not equal to 1. One of the element of generated of I, we assume that one of elements is not pure power. Is the assumption we want to prove that I has this form. We assume that the generated of the I is not the pure power. Assume this one. So then I as a key point in the first of this the first of reminding in today I can be writing a proper intersection of monomial ideas. And this is the contradiction with the is I is the irreducible and this is contradiction. A contradiction. So I does not have the element is this form. So I is equal to x1 I1 and up to permutations. XR up to permutations. Permutation of variables. So this is one of the interesting theorem because every monomial irreducible ideal is known. For monomial ideal is known. So examples. Let I is equal to x1, 2, x2, x1, 2, x3, 2, and x2, 2, and x2, x3, 2. Again, by the key point theorem. Then we write this intersection ideal. This ideal is straightforward because the same of the previous ideals. We have this intersection x1, x2, x1, 2, x1, x1, 2, and so is not this x2 and x2, yes, x2 intersection x2, x3, 2, and x3, 2, x1, 2, and x2, 2. Yeah, the intersection is this. It has this presentation is irreducible, irreducible ideals, and also I is a presentation, a redundant presentation of irreducible ideals. So definition. A prime ideal P ideal P is called a minimal prime ideal ideal of A if minimal prime ideal if I contain P and there is not any prime ideal between I and P. And there is not prime ideal containing containing I which properly contain in P. So we denote the set of minimal prime ideal. We denote the set of minimal prime ideals of A of I by mini R, mini I. For example, if I is equal to power P, P is a prime ideal, power T, T in positive numbers, which P is a prime ideal, then mini I is equal to P because the only P contain A and there is no any prime ideal contain between, there is no prime ideal between P and is no prime ideal in here. And because if there is a Q contain A, so contain P, and this is contradiction. Theory remark. Radical monomial radical ideal. Let me write in here. Radical of radical radical of monomial monomial ideal is intersection of minimal prime ideal. Minimal prime ideals that is I radical I is equal to intersectional he belong to mina I. This is very easily conclude from the previous theorem. We have one lemma from the previous from yesterday and the previous theorem from this today. Radical ideal is the prime ideal. Radical ideal is a square free. A square free is intersectional monomial ideal. Every prime ideal in here is a minimal. So another definition, let M be a finitely generated, be a finitely generated R module. This is the R module is a general definition. R module. R is Noetherian. In here is R is a polynomial ring. Polynomial ring is Noetherian, but this also for the Noetherian is Holt. R module, a prime, a prime ideal, a prime ideal P of R is called an associated prime, associated, called an associated prime ideal of M if there exists an element X M such that P is equal to annihilator of X. This is the definition. This writing in here annihilators. So the set of associated prime uh, the set of associated prime ideals of M is denoted by ACM. So an ideal I of R is called in primary. It's called P primary. P is a prime ideal. Primary if AC R by I is equal to P. Then we said that I is a primary ideas. So fact, let I be a let I be an ideal of R, then mean R is contained in SR. And for here, for simplicity, we write as I instead of instead of as R. So we write as I instead of as R bar I. It means as I is this S. So the following fact, let M be a finitely generated R module, then SM has finitely many numbers. The number of SM is finite. So proposition, the irreducible, the irreducible, the irreducible ideal of X1 R 1 Xi R I k is ideal is a Xi1 Xik primary ideal. Is Ik primary. We find one primary ideals. So proof, let I is equal to Xi1 and Ik and P is equal to Xi1 and Xik. So then P is a minimal prime ideal of I, because the radical of ideal is equal to the P is the minimal prime ideal, is a prime minimal prime ideal of I of A, and so P belong to as a I, because P minimal, and so in here I write the minimal contain in S. So since P power M contain I for M is equal to uh, I 1K. The M is contained here when M is I, the power of this power of pure power, the power of the variables. So we conclude that P is the only P is the only minimal minimal prime ideal of I that is mean I is equal to P. So we want to the S is equal to P. So minimal prime ideal always. So let, by contrary, we want to prove that the S is equal to mean. Let P prime is equal to S I, then P prime contain P. P is contained in P prime because PM contained in here, P prime belong to S, and so P prime I contained in P prime, so P is contained in P prime. And P prime in here, and then P prime is equal to I F is exist. And suppose P prime is not equal to P, then there exists G in P prime minus P. So, and so there is there is there is a there is an element U, monomial U in support G such that it is not divisible divisible by all xij, because in here G belong to F prime. F prime is writing as this one. So GF belong to I. If one of the xij divided U, every element of G, and so this is equal. We have this is not happen. And so we have this one. Divided, then G is a regular element. Regular element on Ri. Regular element, that means Ra means Ra. Ra in this homomorphism, G is a regular element. This function homomorphism is injective. Injective is here R plus I, Rg plus I. This is the injective. This is a regular element. So if G Ft in I, because G belong to F prime and G belong to F prime, we have GF in I. GF in I, so here G plus I, GF plus I. GF to I is the injective, so GF in I. So we have F in I. F in I, and here I F is equal to what? Is a contradiction. So thus contradiction with this assumption. This assumption of P prime belong to S and P prime properly contain P. This is a contradiction. So SN, I is equal to P, and so I is a primary. I is and so thus P is a minimal prime ideal of P, and so uh, uh, this, and so this one is a primary, and so I is a primary ideal. Ideal. And this is my time is finished, and so tomorrow I continue. And if you have any questions, please send email for me. So thank you so much for your attention. Until tomorrow, have a nice day from here to tomorrow. Thank you. Goodbye.